Hello, everyone, and welcome to a new lesson with me. Today, we are going to talk about voltage, power, and energy. So let's go on. I have to teach you these parts. So first of all, let's talk about the voltage. The voltage between 2 points A and B in an electric circuit is the energy or work needed to move a unit charge from A to B. Mathematically, we have this. Wait a minute to write it for you. As you see, this is the voltage between 2 points A and B. You can define it with the differential of work divided by the coulombs, where W is energy in joules and Q is charge in coulombs. C, we use it, okay? As I want to write here, this is joule and this is the coulomb, okay? So it means this. So as you can write this one, it is 1 volt is equal 1 joule per coulomb. Okay, and it shows this is 1 Newton meter divided by coulomb. So thus, voltage or potential difference is the energy required to move a unit charge through an element measured in volts. Okay, here you can see two different shapes. The two equivalent representations of the same voltage V A and B, the voltage between 2 points A and B. Points A is 9. I'm talking about picture A. As you see in picture A, so point A is 9 volts above point B. And in picture B, point B is minus 9 volt above point A. So it shows this, the voltage A and B, or VAB equals minus volt B and A. So you must remember this equation. This is the whole, description and explanation of voltage. Right now, let's go and talk about power and energy. Although current and voltage are two basic variables in an electric circuit, they are not sufficient by themselves. For practical purposes, we need to know how much power an electric device can handle. We all know from experience that a 100-watt bulb gives more light than a 60-watt bulb. We also know that when we pay our bills to the electric utility companies, we are paying for the electric energy consumed over a certain period of time. Thus, power and energy calculations are important in circuit analysis. So, to relate power and energy to volt and current, we recall from physics that power is the time rate of expending or absorbing energy measured in watts. We write this relationship as P can be defined, but the differential of work divided by dt. Okay, so and it shows where P is the power in watts, W is energy in joule, and T is the time in seconds. Okay, so but we can write it and we can develop it. So as you see, P defines to dW divided by dt, and so I can write this dW divided by dq multiplied by dq divided by dt. It means V uh, multiple I. As you see, this is P defines VI. Okay, so this is the equation of all the the relationship between voltage, current, and as you see the power. So, but look at this part, please. Here again, we have two different shapes. As you see, the current here goes through the positive terminal of the element. But here, as you see, the current goes to the negative terminal of the elements. Okay, it means, or it shows, we have two different power. Okay, so can be power can be positive and power can be negative. If power is positive, uh, element is absorbing. But if the power is negative, element is releasing or supplying power. As you see. So right now, passive sign convention is satisfied when the current enters through the positive terminal of an element, and P, as you see, this is plus VI. But if the current enters through the negative terminal, P equals minus VI. Okay, so again, I am writing here for you that can be the P can be positive or P can be negative. So this signs is this the passive sign convention. Okay, and something else that I must write it here for you. If the power is positive, it is uh, absorbed. It is the same as if the power is negative, is supplied. So be careful about these, you know, structures or formula that we are going to use them in, for example, for solving the problems and the equations. So and finally, it shows, in fact, the law of conservation of energy must be obeyed in an electric circuit. For this reason, the algebraic sum of power in a circuit at any instant of time must be zero. It shows this: the sum of power is zero. Okay, this again confirms the fact that the total power supplied to the circuit must balance the total power absorbed. So the energy absorbed and supplied by an element from time t, it means so t1 to t2 maybe is the, or t0 to t1 is like this. This is dw divided by dt. So it shows that the power, I would say, as you see, the energy, so it shows, oh, this is the integration of p dt, and this is the same as integration of vi dt. This is t1 t2 and t1 t2. as you see here. So, but right now, I think we must go and look at this. Energy is the capacity to do work measured in joule. The electric power utility companies measured energy in watt hour, where 1 watt hour, so as you see, it is 3,600 joules, as you see. So right now, look at this part. Example 1. An energy source forces a constant current of 2 amperes for 10 seconds to flow through a light bulb. If 2.3 kilojoule is given off in the form of light and heat energy, calculate the voltage drop across the bulb. So as you see here, we have the current. Okay, we have the current I, and we have T. Okay, and finally we have uh, the energy that we have it too. So the total charge, if I want to say, if you can remember, I is dq divided by delta t. Okay, delta q delta t, and as you see, delta q is I, delta t, as you see here. So it shows that 2 multiple 10 seconds, it is 20 coulomb. Okay, this is I. And the other way, so you know that V is delta W, delta Q, and this is the 2.3, and we have kilojoule. You can multiply that 10 times 3 divided by so 20 coulombs, so it is 115 volt. It is the answer of this part. Okay, so right now let's go to the next part and find the power delivered to an element at t, as you see, equals 3 milliseconds. If the current entering its positive terminal is I, equals 5 cosine 60 pi t, and this is the ampere, and the voltage is 3I. So let's go. You know that we are looking for the power. We are looking for the power. As you know, V is 3I, first of all. 3I, and I is this. It means 3, it means 5 cosine 60 pi t. So as you see, this is the this is the volt of this. This is 15 cosine and 60 pt. This is the volt. Okay, this is the volt of this. By the way, we know that the power is VI. So it is very clear that when you put this, it means 15 cosine, cosine, yes, sorry, 60 pi t multiplied by I, it's 5 cosine 60 pi t. It is that. So we must multiply 15 and 5. So this is 75, I think. Yes. And we have 2 cosines. So it is cosines times 2, 60 pi t. And so as you see this, this is the power of this. Okay. So, But right now, we are going to calculate it when the time is 3 milliseconds. So if t is 3 milliseconds, so we are going to solve this. It's p equals to 75 cosine time 2, 60p, and this is 3, and about the millisecond is time 10 times minus 3. So and when we calculate it, so this is 75 cosine times 2, and this is the 18 pi. So, and finally we understand this number. If you calculate it and use the calculator, so you can see this is 53.48 watts. So, and the last part that we are going to see, how much energy does a 100 watt electric bulb consumed in 2 hours. So you know this, that W is PT, we have it, and the P is 100 watts, okay, and we have time is 2 hour, okay, but we are going to find the second things. It means 2 hour, so you must multiply that 60. Yes, 60 minutes, 70 per hour, and again 60 second per minute, because we need the second. Time must be as a second, not minute, not hour, okay? Because of this we must do this part. So when you multiply all of these numbers together, you can get this 720,000 joule. So it is 720 kilojoule. But we are going to find it for the 2 hours. So the W is PT, and you know this, the W is PT, and the P is 100, and the 2 hour is 200 watt hour. So okay, so I hope you like this lesson, and again we talked about voltage, power, and energy. And if you have any questions, you can comment it. Thank you so much for watching, and I hope to see you next session and solve the other problems. Best wishes, and see you soon. Goodbye.